Okay, so what I'm going to do is to tell you a little bit about the area of research that I'm currently working in, and I want to do it through a specific example, which is the example of the Ising model, which I think through this example you can get a glimpse at what we are doing and several of the interesting aspects of the field. So that's what I'm going to do. So let me start with maybe a video, or not. So what I want to do first is to try to motivate why we work with a certain model, statistical physics model. Very often in a scientific talk, we will bombard immediately the definition of the model. Here I want to kind of cook it up with you in several steps that you understand why, in some sense, we end up with this model. And again, it's going to be the Ising model as an example. So what you start with is an experiment. So this is an experiment done by a mathematician. But since there are only mathematicians in the room, everybody, there are some physicists, don't laugh too much at me. But so when you hit a magnet, what happens is that first you usually burn yourself, at least if you do it with a match. So this was probably the 10th time I was doing it, and the only thing I understood is that I should pre-cook, in some sense, preheat the magnet, because otherwise I burn myself. It took me like 9 tries to manage to reach this conclusion. And on the 10th time, then it worked. What happened is that I reached what we call Curie's temperature, at which the magnet loses its magnetization. So there is a phase transition for real-life magnet at a certain temperature, they lose their magnetization. And you see, you can even, for certain type of magnets, you can reach this temperature even with a match. Okay, and so then the idea is, how can we explain this phenomenon, which maybe for you seems natural, but at least for me, the first time I saw it was not so natural, why temperature has an impact on magnetization. And what we are going to do is that we are going to imagine that our big magnet is made of a huge collection of tiny magnets. In fact, this would be the magnetic moments of electrons in atoms, but this is not going to be important. We are going to think that it's collection of a huge collection of small magnets, and we are going to try to derive the behavior of the model of the big magnet from the interaction between the small components, between these small magnets. And we are going to really think that these magnets behave like real-life magnets. They want to align and things like that. Okay? So first step in our cooking up, we are going to define the object we will work with, what is a magnet mathematically. And what we are going to do is the following. So we are going to say, okay, it's a collection of small magnets. We will call them spins, okay, sigma x. And we are going to make a few assumptions. That's typical when you try to create a mathematical caricature of the real life. You are going to make assumptions. So here we are going to discretize in several ways. The first thing is that we are going to assume that our magnets are positioned on a finite portion of a regular lattice. So we are going to assume regularity in the positioning. It's going to be very useful to have translation invariance later on. So now the position of the magnets is a finite subgraph of, the vertices of a finite subgraph of ZD. Okay? Second thing, and this is actually a much worse assumption, but I'm still going to do it for this talk. I'm going to assume that the magnets, which a priori could point in any direction, actually can take only 2 opposite directions, north or south, +1 or -1 for mathematicians. Okay? So I'm going to assume that sigma x is taking value in +/-1. So that's what I call a magnet. It's just a function from the vertices of a finite graph into +/-1. Okay? And now I need to think, well, what do I want to measure on this magnet? And what I'm going to measure is the total magnetization or the average magnetization. So what I'm going to do, I'm going to just average the spins. So m of sigma is the average of the spins. If all the spins are pointing north, all the small magnets are pointing north, this magnetization is +1. If like roughly half of them is pointing north, half of them is pointing south, you get basically 0 average. And this is something that would not be magnetized. It would not be a magnet. Okay? So that's the first step. It's what is our mathematical object. Now, and this I already mentioned it yesterday for people that were present, we are looking at a very complex system. So in order to understand the behavior of the system, we are going to introduce some randomness. We are going to look at the typical behavior. Okay? So what in physics, if you want to say how likely an object is, you need to first define its energy. And there, we are going to exactly, the energy is going to take into account what I was saying. We are going to think that our small magnets are behaving like big magnets. And what small magnets want to, magnets want to do is to align. So for every pair of neighboring vertices, what I'm going to assume is that there is an energy caused for them not to be aligned. So the energy for a pair of vertices is going to be +1 if they disalign and -1 if they align. So it's going to be minus sigma x, sigma y. Okay? If they agree, I get -1. If they disagree, I get +1. And then the energy of the whole magnet is just the total energy, is the sum of all neighbors of sigma x, sigma y. So you note that here I'm again making another assumption, which is that the magnets will only talk to their neighbors, try to align with their neighbors. This is, you may think it's a strong assumption. I will come back to this later on. But what is clearly reasonable is to expect that they will definitely care about their neighbors much more than other small magnets. So in first order approximation, it's reasonable to expect that it's only going to align with the nearest neighbors. Okay, and once you have this energy, h lambda of sigma, then the probability of a magnet is going to be proportional to exponential of -1/t times the energy. That's what you would get naturally. For instance, if you define the natural dynamics on the thing, it will converge to a measure that will have this form. And here the important thing is that the higher the energy, the smaller the probability, and how much you care about it is encoded in this parameter 1/t. So T is going to be interpreted as a temperature, right? The larger the T, the less you care about the energy. If T is infinity, you don't care at all. It's a uniform measure. If T is 0, you will actually get just a measure that is going to be a sum of Dirac. Either everybody is +1 or everybody is -1, okay? And in between, well, that's going to be where things start to be interesting. Okay, when you do that, there is one thing that you can measure now. It's the average magnetization. I average against my measure the magnetization. And here the problem is that, well, it's pretty clear what you get. You always get 0, whatever the temperature. And this is extremely simple to see. It's just that a magnet and its full reverse get exactly the same energy, hence the same probability, but opposite magnetization. So you always get 0, so in some sense it doesn't explain anything about having a magnetized phase or unmagnetized phase at this stage. But in some sense the reason why it gives you 0 is because we didn't really dive into the core of the systems. Here we didn't break the symmetry. There was a symmetry, and very often in nature the symmetry is naturally broken by the environment. For instance, maybe your magnet is in a magnetic field. Maybe a tiny one, or maybe it was in a magnetic field at some point. Okay, so here I want to break the symmetry, and it's going to be the third step. So definition of the model, then introduction of randomness. Now I'm going to break the symmetry, and so I'm going to do it like as follows. Don't look at the video. I know it's hard, right? This is really something I didn't do on purpose, but I completely forgot about this video the first time I gave this talk, and I noticed that everybody was completely mesmerized by this red dot. So now I always keep it because I'm thinking I'm always laughing at cats, but we are all cats, right? You are all looking at this red dot and try to see where it's going. So anyway, when I would be 65, I would still be making this joke and thinking, but I will still be mesmerized by how much we like red dots. Okay, so what I'm going to do now to break the symmetry, I'm going to do something I know there are physicists in the room that is not so natural, but mathematically it's going to be equivalent, and for the sake of this talk, it's simpler to do it like that. What I'm going to assume is that in some sense the environment is forcing the spins on the boundary of my magnet. Remember that the magnet is finite. It forces them to be +1. to align with the magnetic field that will be pointing that direction. It's not so natural because, in fact, if you would be in a magnetic field, all the spins would be impacted. But at the end, you end up with the same object, so let's not dive too much into this consideration. So let's look at the measure, the same measure as before, except it's conditioned on the boundary spins to be +1. So now you see that you don't have the flip symmetry anymore. Of course, you can flip all the spins inside, but not those on the boundary. So then the energy will actually be different because there will be the energy of the contribution of spins which are just one step inside with exterior spins. So you don't have the same symmetry breaking, and you have to trust me, but when you look at that, then the average magnetization with respect to this measure is strictly positive. And in fact, at every temperature. So in some sense, I didn't fix the problem, I just made a new problem, which is that now it's always strictly positive. But it's because I forgot one thing. I mean, strictly positive, especially when you think as a physicist, can be basically 0, right? It depends how close to 0 you are, and that's where, in some sense, the size of the magnet is going to impact. The size of the magnet being very big, maybe this strictly positive is for certain temperature extremely close to 0, let's say even exponentially close to 0, and for others, it's going to be very large. So here what I'm going to do to fix this problem is that I'm a mathematician, so very big for me means infinity. So I'm going to just look at the limit when I take the size of my magnet to infinity, when I take lambda to ZD. Okay? So now I get a new quantity. Let me call it m star of t. So it's the limit of this magnetization in finite volume. And there you will agree with me that this may be strictly positive, this may be 0. I have no information about that for now. Okay? And that's going to be the whole, core of the discussion is to study this m star of t. Okay, so this m star of t, it has a cute name. Cute, I don't know, but it has a name. It's called the spontaneous magnetization. The idea is really that it's what you get when you immerse a magnet in a magnetic field and then remove the magnetic field. Then it's what remains. And here, just there was a fourth ingredient, right? I broke the symmetry and I took the infinite volume limit. And if you think about it in statistical physics, almost every time you do things of this kind. You define your model, you introduce randomness, you break the symmetry because very often you have to do it if you want to really look at the behavior of your system, and then you take the infinite volume limit. And for people who think that, oh, well, but it's strange to be taking a quantity that is an average of, when you do it like that, in fact, the average is, the measure is ergodic. So the average is actually what you will get almost surely. All the magnets will have an average, average in space, like magnetization, which will be m star of t. Okay? That's the end of the first part of the talk. So you survived it. Congratulations. Or for those who didn't fall asleep. But now let's dive into the second step, because at this stage I didn't tell you at all how this connects to the natural experiment. So what I would need to do now is to try to explain why the Ising model is actually mimicking what we get in real life. And in real life, we have this Curie temperature, distinguishing between a phase with spontaneous magnetization and a phase with no magnetization. So do we get this for the Ising model? By the way, the temperature, the Curie temperature for magnets, we call it the critical temperature in statistical physics in general. And it will be distinguishing between what we call a ferromagnetic phase and a paramagnetic phase. So do we get that? And here it's maybe a good point to tell you about the history of the Ising model, because it's a fairly interesting history from the point of view of both mathematics and physics. So the reason for which it's interesting is that it really started extremely poorly. So, it's a good advertisement that you should persevere. So the Ising model is named after Ernst Ising, who was a PhD student of Lenz. He was not the person who introduced the model, at least that's what everybody says. I kind of agree with that, but let me be honest with the fact that the first time we see the Hamiltonian of the Ising model is in the paper of Ising, not in the work of Lenz that was a little bit prior to Ising. So Ernst Ising introduced, or at least the Hamiltonian, worked on the one-dimensional case, which is basically a very simple exercise by modern, I mean, you can really give that to an undergrad, and it's not so difficult to see that, well, on Z, the critical temperature is 0. Meaning as soon as you tune the temperature, you have 0 spontaneous magnetization. So in some sense, one-dimensional Ising magnets do not exist. They are always, they magnetize. So that was a pretty bad start because, I mean, if you want to explain ferromagnetism, you would like to have this critical temperature, which is strictly positive. So at the time, Ernst Ising was pretty depressed about this, this discovery. And he, in some sense, he even felt that the whole PhD was a failure because he left academia and only learned way later that his name was one of the most cited names in physics, in modern physics. So he really discovered it when he was like, I think even after Second World War, so more than 20 years later. The poor Ernst Ising, in addition, made a very wrong, actually, prediction. He thought that this was always 0. Well, sometimes you are wrong. And a second thing that was probably, I would say, even by the time, much more troublesome, because at the end, you know, he made a prediction, but there was no proof of what was happening in higher dimensions. So, you know, the prediction could still be wrong. But something that was more troublesome is that Heisenberg introduced at the same time, and you have to put into emphasis that this is the 20s, it's one of the golden ages of quantum physics. And Heisenberg introduced another model for ferromagnetism, which is really based on quantum physics. And we know that electromagnetism is a quantum phenomenon. So there was a very big problem with the Ising model, a deep-rooted problem about which you cannot do anything, which is that it's a classical model. So in some sense, this was a much worse, it was much more worse of a news than the actual prediction of Ising in the first place. And this introduction is like 1928. I mean, this is not the year Heisenberg was born. So that was a bad thing. But what happened is that a few years later, Rudolf Peirce, in two ways, kind of saved the model, at least for a few years. So the first thing that Rudolf Peirce did is that he proved that in fact, Ising was wrong. In any dimension larger or equal to 2, Tc is strictly positive. So you have a phase transition. In fact, seeing that it's not infinite is not so difficult. So it's really in between 0 and infinity. By the way, you can, with modern tools, you can try to play a little bit with the model and ask yourself what happens on graph which have a dimension which is not an integer. You know, take a graph with isoperimetric dimension d, which is strictly larger than 1. So in fact, we believe that as soon as you have strictly larger than 1, you have a phase transition. The best thing that is known, because of course, if you take this graph, they are not translation invariant. The best thing that is known currently is that for d larger than 4, it works. So you get a worse result than on ZD, but you do not assume translation invariance. On any graph that has isoperimetric inequality d larger than 4, you have a strictly positive and finite phase transition, a critical parameter. Okay, so just to say that because it should be for any d larger than 1, really only the linear growth are giving you basically Tc equals 0. But so to go back to what Rudolf Peirce did, he did a second thing, and this was probably an even more important thing. So what he did is that he noticed that at the same time, basically, there were modelization of other phenomena, not the magnetism, for instance, binary alloys or certain like cooperative phenomena. And all these models for these other phenomena, they were in fact just the Ising model. For binary alloys, maybe the people were saying that there were two things like A and B molecules or atoms, or in the cooperative phenomena it was maybe 0, 1, like are you agreeing or not? But it was at the end, after a change of variable, the Ising model. So what this illustrates is that a statistical physics model, even though it can be a pretty poor description of your actual physical phenomenon. I mean, I'm not going to lie to you, the Ising model is a terrible model for ferromagnetism. It's really, this is not a good model. But through the universality, in some sense, of its description, the fact that you lie higher, from a higher altitude, well, certain different phenomena that looks very different in a lab can relate to this master model pretty accurately. So this is something quite interesting about the Ising model, but about statistical physics in general, is that in some sense there is a trade-off. The model may be simpler, more naive if you want, but very often when they get more naive, they also kind of describe several aspects of several different phenomena, and that's what makes it interesting. So these two things kind of saved a little bit the Ising model. Maybe it didn't make it, the most studied model in math or in statistical physics in general, but it definitely saved it, and it saved it for sufficiently long time then true revolution happened. And this revolution is due to Larson-Zager in 1944. Larson-Zager liked to first state the formula, wait 2 years for everybody not to manage to solve it, and then explain how you make how you prove it. So that's what he did, and that's why there are two numbers, 42 and 44. So what he did, Larson-Zager is a chemist. So what he did, a very famous chemist, getting Nobel Prize for actually something completely different. And what he did is that he computed the free energy. So the free energy is, as I said, when you sample your magnet at random, you may actually think, of course, its energy is not well defined, right? Because it's an infinite sum of +1 and -1. But you can look at the mean, at the mean energy per unit of volume, and this is the free energy. And what he did is that he computed this free energy explicitly on the square lattice. He got this formula, which I'm happy. Usually I give this talk on a board, but I realized yesterday that there was no board, so I was very happy to have slides. And this is usually the main difficulty for me, is that I never remember this formula. But so that tells you that something about my memory. But anyway, so this is the formula for the free energy. It is what it is. The important thing that you need to remember is that it exists. Okay, there is an exact formula. Pretty simple, actually, compared to the complexity of the system, for the free energy. And maybe, so by the way, the formula was, the derivation is quite complicated in the original paper. It was simplified by the postdoc of Larson-Zager, Bruriya Kaufman, a few years later. And from there, actually, it's a beautiful odyssey, because there have been many different derivations of this formula. It's a very cool example where different fields of mathematics, combinatorics, algebra, analysis, you can choose your favorite field, and probably if you work hard enough, you will manage to reprove this formula. It's really, it's a beautiful thing. There is even a paper which is called the 399th solution of the Ising model, which means the 399th derivation of this thing. And it's a slight exaggeration, but I would definitely not be surprised if there are at least 20 derivations that are sufficiently different to be called different. Okay. But here maybe I was not so nice, because I introduced a new player, this free energy. So let me rephrase in this context in terms of the actual player that I introduced for you, which was the spontaneous magnetization, m star of t. And basically, a few years later, Chen-Ning Yang, this is a Yang from Yang-Baxter, Li Yang, Yang-Mills, I mean, well, the Yang, I mean, one of the Yangs. and what he did is that he really like massaged the techniques of Lars Onsager and Breuer-Kaufmann much more, and in some sense from there you manage to extract even the spontaneous magnetization. It's not at all, the formula is quite simple, especially compared to the free energy, but the derivation is really, really very difficult, the original one. So Chen-Ning Yang actually described it as the hardest derivation in his career, which is maybe a slight exaggeration, or maybe it was only in 53 that he said that, but so definitely it's a very difficult result. And from that, there is one thing that you see immediately, there is a plus part, okay, a positive part, and so that tells you that this spontaneous magnetization is strictly positive as long as t is smaller than 2 over log 1 plus square root 2. So you can compute explicitly the critical parameter. It's definitely not the simplest way of computing the critical parameter, but that's a way of getting it. So in 2D, you can basically compute everything explicitly for the Ising model. Not everything, but many things. And here, I want really to advertise one thing, is that it works on Z2. It's based on what we call integrability, and integrability is a very versatile property. It breaks down extremely easily. So it's also working on any, in fact, planar graph, but as soon as you get rid of the planarity, the thing collapses entirely. So for instance, let's say I go back to my assumption of nearest neighbor. And let's say that I assume that I'm not just interacting with my nearest neighbors, I may be interacting with the next nearest neighbor. But just my interaction is extremely weak. You know, 1 over billions of billions of billions. Okay? Whatever the epsilon for the interaction, so you put plus minus epsilon depending on whether you agree with next to nearest neighbor, you don't get any integrability. Everything breaks down. Okay? So a very, very, very difficult property to maintain. And in particular, one thing which is clear is that this is a property that is not valid in 3D, at least in our current knowledge. The 3-dimensional Ising model is not integrable. And personally, I don't believe it is, but because I like to do things when it's not integrable, which I know it's maybe something I should not be saying in front of this crowd, but yeah. So what do we do now? So we have a phase transition. That's what Peirce proved to us in dimension 2, 3, and more. What do we do? So in dimension 2, we have everything explicitly. What do we do in dimension 3, which is the dimension of our experiment, right? The real-life magnets are 3-dimensional. So one thing we would like to do is to be able to prove that the phase transition is of the same kind as the phase transition in real-life magnets. And in real-life magnets, when you plug the spontaneous magnetization, you can measure this. This is actually a plot that is coming from the work of Curie. It's Pierre Curie, by the way, in this case. And what you see is that the magnetization is continuous. It definitely goes down to 0. In fact, it's a finite thing. So, of course, it is continuous in finite systems. But it's really, we can see that it approximates more and more something that is going to be continuous, but have a singularity at the critical point. It will look like what we have on the right. And notice that if I would plug again m star of t from the previous slide, and you ask, I don't know, your very young sister or brother, or I mean somebody in high school to do an analysis, you will see that it's continuous and that it behaves actually in a singular way like t minus tc to the 1 over 8. Okay, so you have a very interesting behavior in dimension 2, but do you get the same in higher dimension? So that's going to be the new question here. And what I want to be doing is to explain to you, I mean, it's not a full proof, obviously, but to give you an idea how you can prove that in 3D, while you completely lose integrability, you can still manage to get continuity of the phase transition. By the way, it's very, I mean, I was a little bit surprised that after everything we know about the Ising model, nobody tried to do that before. That was a little bit of a surprise. So with Michael Eisenman and Vladas Sidoravicius, we proved that in 3D, the spontaneous magnetization at the critical point is 0, but in fact, it's exactly the thing that you need to prove that it's continuous. So if it was discontinuous, it will drop to a certain strictly positive value at Tc, and then, of course, it would get to 0 above Tc. Is just what you get by definition. So the only thing that you don't know by definition of the Tc is what it is equal to at the critical point. And if you prove that it's equal to 0, then you have continuity of the phase transition. So that's what we did here. And in order to give you an idea of the proof, I want to tell you a little bit about a new player in the game, which is called the spin-spin correlations. So the spin-spin correlation is just a measurement of how things align, like how much spins are correlated at large distances. Okay, so it's just the average of sigma 0, sigma x. You can look at the plus measure. You can look at the measure without symmetry breaking. You take whatever you want. And again, you look at the infinite volume thing. Okay? Okay, so at large scales, there is something extremely natural to expect is the following. So your two spins, you will expect that they will become independent when you send them to infinity. I mean, to infinite distance. And so in particular, if you take the plus measure, if you send them to infinity, then the spin-spin correlation should converge to the average of each one of them. So 1 squared, because it's translation invariant. And in fact, I define the spontaneous magnetization as a space average, but by ergodicity, it's the same, ergodicity and translation, it's the same as point average. So in fact, the average of sigma 0 or the average of sigma x alone is just the spontaneous magnetization. So then it's natural to expect that the spin-spin correlation is going to converge to the spontaneous magnetization squared. And that's what happens. Okay. But there is another thing which is actually quite interesting, is that if you look at Tc, in fact, the spin-spin correlation goes to 0 when you don't put the symmetry breaking. The reason is that in some sense, the symmetry breaking, the measure is kind of continuous from the right in some sense. So for T larger than Tc, clearly the things are going to 0 because the spontaneous magnetization is 0. And in fact, you preserve this property when it goes to Tc. It's not so easy to prove, actually. You need something. It's called the infrared bound. I don't want to be telling you about it, but the only thing I will tell you, which I know that I'm going to make enemies by saying that, is that it's quite old. And by quite old, I mean older than me. Okay, so everything that is prior to 1985 is young for me, is old for me, and everything later is young, like me, including 85. So this is like going back to the 70s. You can prove that this spin-spin correlation go to 0. So there it looks pretty simple, right? I mean, you just plug T equal Tc and you get spontaneous magnetization equals 0. But there is a subtlety, and I'm happy to be almost big enough, tall enough. So here there is a plus, and here there is nothing. It's not the same measures. A priori, the plus and the free, what we call the free measures, are not the same. And in some sense, it's exactly the core of the argument. I will need to prove that the two measures are equal, that the correlation for plus boundary condition are the same as the correlation for free. And here I really want to maybe say something that is obvious for everybody, but I'm going to say it anyway. When you look at a discontinuous phase transition, the typical thing that happens in the discontinuous phase transition, it's not always the case, but the typical thing is that there are different states of matter at the critical point. If you take water, you go to 0 degrees, you have coexistence of ice and water, right? So exactly if you want to prove continuity of the phase transition, it's not so surprising that you have to rule out the fact that you would have different state of matter. And that's exactly what we will need to do here. We will need to prove that these two measures that kind of correspond to state of matter are actually the same. Okay, so we reach something. I don't know actually what time it is, but we reach half, not really, but let's say half of the talk. Don't worry, it's less than half, it's more than half. Don't worry, I was talking to myself. So I'm going to do a small trou normand, as we say in France. So I'm going to, it's this thing that you drink very strong alcohol just to get rid of everything you ate up to this point. It dissolves everything, and you can have a second dinner, starting with cheese. So here, it's something that has going to be nothing to do a priori with the Ising model. Okay, so forget about everything. Wake up if you were falling asleep. And I'm going to tell you about something that I actually like much more than the Ising model, but don't tell the people working on the Ising model, which is percolation theory. So in percolation theory, the game is totally different. You want to understand porosity of a medium, and you are going to do it by basically modeling not the water, the liquid or the gas that is pouring through the medium, but the medium itself. And you are going to think of it as a random maze, or if you prefer, as a random graph. So you take ZD, and you pick a random subgraph of it. And for instance, what you can do is that every edge, you include it in your random subgraph with probability P, and you remove it with probability 1 minus P. You get a new graph, and you look at the connectivity properties of this graph. So it's called Bernoulli percolation in this case. And for instance, what you get is the following when you make a simulation. So this is P. So I apologize for people that were here yesterday, but you chose to be here today. So or you didn't because your advisor is here, but that's not my problem. I'm not the advisor of anybody here, so that's fine. So here it's a simulation for P equals 0.495. Here it's a simulation for P equals 0.505. Okay? So extremely close to 1/2 for both of them, one slightly below, one slightly above. And the colors are the connected components of my graph. They correspond to the connected components. Here you see that you have only very small ones, while here you have, it's not an anomaly, there is a huge one, the red one. Okay? And so there is a transition between a phase. In fact, if I would have an infinite system, here this red thing would go to infinity. There will be a unique infinite connected component. While here you will get only finite connected component just by the fact that everything is random, you will get very far some big connected components, but basically the largest one in a box of size n will be logarithmically big. So very, very big phase transition, the sharp phase transition between the two phenomena. Let me just jump this because otherwise I will never get to the end. But now what's the connection with the Ising model? The connection with the Ising model is that percolation, when you don't have integrability, saves you in the following way. That when you look at the correlation of the Ising model, they get rephrased as connectivity probabilities for a certain percolation model. This percolation model is not the Bernoulli percolation that I mentioned before. It's actually a much more complicated one. It's called the random current representation. But basically, the spin-spin correlations are rephrased as the probabilities that 0 is connected to x in my random graph. Okay? And when you get a dictionary between different models like that, percolation on one side and Ising on the other one, very often it's actually just not one quantity that is related, it's a bunch of quantities that are related. And here in particular, if you look at the plus correlations, actually they are equal to the free one plus something that gets rephrased in terms of the percolation model. And the rephrasement is that 0 and x are connected to infinity. But now something pretty natural happens is that in the previous picture, when there was an infinite connected component, it was unique. And that you may think, it's a different percolation model, but you may think that this is something very hard to break. That usually in percolation models, when you have an infinite connected component, it's going to be unique. And it's the case for the random current representation. So what you get is that if 0 and x are connected to infinity, they are also connected together. They are in the same connected component. But if they are connected together, then the second term is smaller or equal to the free correlations. So the plus boundary condition correlations is smaller than twice the free one. the free one go to 0, the plus 1 go to m star of t, tc squared. So you get that this m star of tc squared is 0. I'm not going to lie to you, I lied to you. I mean, I did simplify a little bit the story, but not that much. In some sense, I think that this paper with Michael and Vladas helped us realize that there was really the connection between this percolation model and the spins model that you get, like the Ising model, was really understudied for many years. And one of the reasons for that, so here you see, I mean, in some sense, once you have the connection and you use it well, it's really a question of drawings. Huh? So that's kind of, on this side, I almost didn't lie. But what happens, the reason why it was maybe not studied so much is that the percolation models that you get typically when you look at a spin system and you look at the percolation model connected to it are percolation models that are not independent. So Bernoulli percolation that I defined just before, the fact that your edge is in the random graph or not is independent for every edge. And that you think, you know, that, I mean, well, we all know that independence is something cool. I mean, at least it's something that helps us quite often. And these models that come from the world of spin systems, they are not independent. So what happens is that very, very clever people, many physicists in particular, did manage to say very interesting things on these models by proving that they were also integrable in some sense and computing things explicitly on these models. What was much harder was that the mathematician didn't in some sense manage to handle this percolation model with dependencies, so they were lagging behind. In some sense, if you could use, there was already like many things used with percolation models, just because physicists in particular and mathematicians later on were able to compute things explicitly using integrability, but as soon as you were getting away from the integrable world, there were difficulties because on the math side, we didn't really know how to handle this percolation model with dependencies. This changed a little bit in the last 15 to 20 years, and that's why, in some sense, a whole class of new results emerge from this bridge between spin systems and percolation models, because now we understand these percolation models much more. Okay, I think I still have a little bit of time. Actually, I absolutely don't know how long I had in the first place, so I'm going to just act like I have more time. These, by the way, are 3 drawings. Upstairs, it's a model, a percolation model that I like very, very, very much. It's called the Fortuyn-Castellane percolation. It's a model that is related to the Ising model, another percolation model related to the Ising model. This is just a continuous percolation model called Boolean percolation, just to show that sometimes you don't want to be working on a graph. In some sense, what you really want for a percolation system is to be a question of studying the connectivity of a random object, a random set. And this is actually one that I think is very, very interesting. There is a way of defining percolation model by taking a random function and looking where it's positive or negative. And you have many, many ways of sampling this random function. And for instance, one of the ways is to look at random combination of eigenfunctions of the Laplacian, or looking at a random, just a randomly chosen eigenfunction of a random operator, what we call an Anderson operator, or a random Schrödinger operator, say. And you get very, very interesting nodal domains, and you can look at the connectivity of those things. So large-scale properties, very different from what you usually do, which is usually trying to count the nodal domains or things like that. Here you will be interested in like large-scale connectivity properties, and there are very deep connections, in particular with Bernoulli percolation. Okay, so in the last few, it's a 50 minutes talk, 55. In the last 10 minutes, I'm going to just tell you about what you do next. So once you prove continuity of a phase transition, the good thing is that that means that you have critical behavior at the critical point. And this is where usually physics starts to get really exciting, because at a critical point, you have emergent laws. And here I want to illustrate that by studying, in some sense, the next level of I'm just taking a bigger lens, and I look at the spin-spin correlation not between 2 points, but between two endpoints. If you take 2n plus 1, you will get actually 0. So let's take two endpoints, and let's look at these correlations. Okay? And I want to say two things about it. So I'm going to look at the dimension 4 model, because there are two emergent laws that are interesting in this model. And the first emergent law is something that we obtained with Michael Eisenman a few years back, is that if you fix dimension 4 and you look at the critical parameter, t equal tc, then the spin-spin correlations, they start to behave at large scale like a Gaussian field, meaning that the spin-spin correlations are going to satisfy the bosonic rules, or the Wick rule, if you prefer, in probabilistic terms. Of course, it's only going to be approximate. You need the distance between the points to go to infinity. But if the distance goes to infinity, you really get an approximate Wick law. Rephrased in terms of, you could look at this sigma x as a field that you test against a smooth function. What it tells you is that this testing function is going to get, when you go larger and larger smoothing, it's going to get to a Gaussian field. This is a very interesting thing, because you see it in some sense it allows you to reduce the question of studying the whole scaling limit to the question of studying the two-point function. So it's a very big simplification. I mean, very often, in particular in conformal field theory, what you try to do is actually to get to the higher order correlations from, the structure of the two-point function is basically trivial, but it's getting to 4-point, 6-point, etc. that becomes very difficult. Here, it's trivial. That's actually what the name is called. So it's not so pleasant to be proving something where, the result is triviality. You prove triviality of something. So just to tell you a little bit of history, so in dimension d larger than 4, this is actually an old result by my standards, again. Eisenman and Fröhlich independently in 1982 proved this, where the equivalent sign here is actually 1 plus big O of 1 over distance to the d minus 4, so polynomial rate of decay. In dimension 4, you get logarithmic rate of decay. So it's something a little bit more subtle, and it's due to the fact that this is a critical dimension. If you go to dimension 3, you will not get triviality. In fact, if you even gear your model to have an intermediate dimension between 3 and 4, any dimension smaller than 4, you will get non-trivial. So it's really the critical dimension. And the connection it's called triviality because the proof actually works for the Ising model, but it works for a large class of models called the 5-4 models. And these 5-4 models are natural discretization of what you would like to do as a field theorist if you want to introduce a model with a field theory that would describe two particles in interaction. You would like to introduce a 5-4 interaction. And when you try to define this properly, because if you just look at the integrals, they all diverge for different reasons. If you want to discretize and make it properly, what this result tells you is that when you discretize, when you take the limit, you get something trivial. You get the Gaussian field. So the 5-4 interaction disappears. So you don't know how to construct this interaction by this kind of discretizations. Okay? That's also, by the way, a good example. So you may think that the dimension 4 Ising model, maybe I kind of started telling you, oh yeah, let's look at dimension 4 Ising model. You may have thought, okay, maybe this is not an interesting model. It's not physically interesting. But actually, it's probably even more interesting than the 3D thing because it's for the 3 space and 1 time dimension, basically. There is a connection with quantum physics. And yeah, actually, I'm going to finish on that. Just tell you about the connection with percolation again. So what happens is that, let's do one thing. Oh, I don't know why there is free everywhere, but okay. I know why. I wrote it and forgot to remove it. But so forget about the free thing. So let's say that I take 4 points, okay? Trust me, in fact, if you do it for 4, the 2n thing follows the same. Take 4 points, and let's look at the difference between the 4-point correlation and the Wick law. That's going to tell me how close my 4-point correlation is from the Wick law. In fact, when you look at the percolation model, you have a very nice rephrasing of this quantity. It's actually equal to -2 times basically the 2-point correlations times the probability of the following. So let's say I take the 2-point correlation x1, x3 and x2, x4. Okay? So then I'm going to get the percolation model condition on x1 being connected to x2, x3 I said, sorry, x3, and x2 connected to x4. So I'm forcing my graph to have a connection between these two things. And basically, the difference between the 4-point function and the Wick law is going to be conditioned on this: do I intersect or not? Or are all the 4 points connected or not? They are not necessarily connected, but are they or not? And here, there is, I mean, once you see that, there is, I don't know if I should be, I don't know if I should be doing that, maybe. There is a good analogy. This percolation path, in some sense, you should think of them as random walks. They are not random walks. In fact, they are very, very non-Markovian if you think of them as random walks. But think of them as random walks nonetheless. Okay? If you think of them as random walks, there is a very cool result about random walks. It's a fairly easy one, actually, which is telling you that if you take 2 random walks going between the points at mutual distance L, in dimension 5 and more, these things do not intersect, but they really do not intersect heavily in the sense that the expected amount of, the expected number of intersections is going to 0, even very, very, very fast, like 1 over L to the d minus 4. In dimension 3 and less, these random walks will intersect with positive probability. And in dimension 4, the expected number of intersections doesn't go to 0, but the probability of intersecting goes to 0. So here, in fact, the goal of, I mean, the whole difficulty of the proof of this theorem is to be saying, I have this analogy, if it was random walk, then the theorem is just saying then dimension 4 should be the critical dimension below which this probability should not go to 0, hence the 4-point function is not close to the Wick law, and above which it should go to 0, and therefore you should have approximate Wick law. The difficulty is that it's not random walks. So the 40 years discrepancy between the result in dimension 4 and strictly larger than 4 and dimension 4 comes from the fact that if you look at the expected number of intersections, in fact you have very cool formulas using what we call the infrared bound again, that basically bound the expected number of intersections is smaller than for random walks. And this is kind of due to the fact that these random walks, in some sense, these clusters, in some sense, they look much more like self-avoiding walk type objects. They would like to avoid each other. So they actually would like to intersect even less than random walk. But of course, I mean, it's not easy to prove. But in dimension 5 and more, you can use these formulas for expected number of intersections. You get the result pretty smoothly, actually. It's a these are the proof by Eisenman and by Fröhlich are absolutely beautiful, but they are in some sense fairly elementary. In dimension 4, looking at expectation is not going to be sufficient, so in some sense you have to dive into the stochastic geometry of this path. And there, in some sense, you are looking at 4-dimensional self-avoiding walk in some sense, and you want to be understanding what they are doing. That is, unfortunately, or fortunately, I don't know, much harder, and that's what explains the difference between the two things. I didn't have time, like always, basically, to reach the last, the very last step. So I will not. Don't worry. My plan is not. I should not even be doing that. Let's say this was the end of the talk. No, what? No, stop. Computer, listen to your master. No. Okay. So basically, the last part was that this Gaussian emergent property is very nice, but then it really leads you to the natural question of, now can you actually understand the two-point function? And there is another emergent law that, there are also, there are new emergent laws that appear, and these emergent laws are symmetries. This two-point function should be, in fact, translation invariant, scale invariant, and rotation invariant. And if you plug all of that together, you realize that this two-point function should behave like 1 over x to the d minus 2, where 1 over a Euclidean distance of x to the d minus 2. Once you have that, you end up with a limit which is called the Gaussian free field. So you can fully describe the behavior of the 4D Ising model. So what was, in some sense, a negative result from, in the first place, this triviality result looked like a no-go result from the point of view of field theory, because it tells you cannot discretize in order to get a non-trivial field theory. You need to go to gauge theory and things like that. It's actually a very positive result from the point of view of statistical physics, because then you can hope to be describing fully the limit. And this is a work that we are hoping to complete with one of my PhD students, Romain Panis, to actually get the full Gaussian free field convergence. Thank you very much for your attention.